Hey guys, welcome back. We have finished the last assignment from our chapter, so now we're just going to do a quick review over Unit 7. Expect we will have, the next thing we'll be doing is a practice test a practice quiz over regression, and then we'll take a quiz. So we're going to do the attendance versus wins is one of the things we're going to be looking at here, and we're going to jump right into the assignment. So 38. Attendance for 2010. In the previous chapter, you looked at the relationship between the number of wins by an American League Baseball team and the average attendance at their home games for the 2010 season. Here's a scatter plot, residual plot, and part of the regression analysis. So here we have our scatter plot. So we're plotting the wins versus the attendance. So we're trying to see, we believe that the wins are going to help us explain the response variable, which is what we're interested in, which is the attendance. And then we have our residual plot. So this red line here is going to be the model itself. Any point that's above it would be a positive residual, which would mean that their attendance was greater than what we would predict by the model. Any value that's below it is going to be a negative value, which would tell us that it's when their attendance was less than what the model would predict for the amount of wins that they had, right? Okay, do you think a linear model is appropriate here? So when we graph out the scatter plot, this looks positive, so it looks like in general it is increasing, right? It's pretty weak. I mean, there's a whole lot of spread here, a lot of variation going on. It's not tightly clustered around the line itself, but it is still positive and it looks linear. I suppose you might be able to say it's curved. Anyway, whenever you look at the model over here. Okay. Whenever you look at the residual plot, this helps us to see if we have any, there's curvature, and we're really just looking for any pattern at all. In this case, we have something that we would call a fan, so fan behavior. So as we increase in the x value, so this would be like our x. This is our x bar, so our average x. As we increase in our domain and as we get further away from the average in the positive direction, our model kind of tends to break down. So at the very beginning of our domain, the model is really accurate, and then as we increase, the variation is going to increase as well. So this is actually kind of typical for models to kind of break down as we get further and further away from the mean, but also further and further away from the domain in general. All right, part B says interpret the meaning of the r squared in context. So this is going to be the, what do they call that? I'm sorry. The regression analysis. Yeah, so the regression analysis comes from the computer. So the regression analysis is going to give us the r squared, our variables, and the coefficient. So if we look over here, we have constant and wins. So it's kind of weird. They're saying the dependent variable is the home attendance. So that's what we're trying to measure. That's our response variable. Okay, we usually use response variable, not dependent. And then over here for the variable, the constant is going to be the y-intercept because that's the one that's constant. That's not the slope. And wins is going to be the slope for, and wins is going to tell us that that's our explanatory variable. So here we have a y-intercept of negative 6,760.5 and a slope of 341.22. All right, so our r squared is 28.4. So 28.4% of the variation in the response variable, which we said was attendance, can be accounted for by the model with wins, which is our explanatory variable. So this is just a general form. So right here you have your r squared, whatever your coefficient of determination is, which is just the correlation squared, by the way. And we'll do that in the next problem too. The variation in the response variable can be accounted for by the model with the explanatory variable. So that's just a general form of how you'll always answer that question. So just kind of get that in your head. All right, do the residuals show any pattern worth remarking on? Yes. So the pattern we do see here is like fan behavior. So as our domain increases, our model kind of falls apart. We have more variation in our residuals. Okay. The point in the upper right of the plot is the New York Yankees, so that's going to be this one right here, and it's also the same thing shown here. If you notice, I mean, the residual plot here is really similar to that. It's just you're taking the values for whatever you have here, and then you're drawing a line going straight up to here, and that's going to be what's being graphed out here. So this point here going, how much higher is it? The actual from the predicted, so the residual, this is a residual, is equal to the actual minus the predicted, which is going to be this line here. And it's actually, you could try to predict what these values are going off over here. and then the same thing from here, and then try to figure out how far apart they are. But the easiest way to do this is actually look at the residual plot, and if we go across here, it looks like it's going to be close to about 13,000. So we have a positive residual of about 13,000, which means the Yankees had somewhere about 13,000 more fans in attendance above what we would predict for them based on the number of wins that they had. They did have one of the highest winning seasons or highest winning records. There was only one team that was above them, and that team that was above them, which is kind of odd, had a negative residual, which means that they had far less. The actual was far less than the predicted that from the model. So they had a negative residual, which is kind of interesting. That definitely does not help our data out. Okay, so estimate for the residual for the Yankees is going to be a positive 13,000, or it's just an estimate, but close to that. All right, 42nd inning. Consider again the regression of the average attendance of wins for the baseball teams. What is the correlation of wins and average attendance? Okay, so if they give us the R squared, actually the correlation is a part of that as well. So what we're going to do is we're going to change the R squared to a decimal from the percentage. So just move the decimal over twice. That is really important before you take the square root, okay? If that's what R squared is equal to, how do we get rid of the squared? Well, we take the square root of both sides, right? Remember, the square root's really the 1/2 power, and so the half power of a square is going to undo each other, giving us just the first power. So R is going to be the square root of that value. So I'm going to do 0.284, and then the square root. So I'm going to hit the caret button, which is right here, and then 0.5, and that's going to give me my correlation coefficient. Okay, there we go. Just double checking. Yep, that's it. I did round it, but that's fine. All right, so our correlation is going to be 0.53, which is pretty weak. Again, remember we said values that were around 0.6 or lower for the correlation was weak, but that's just kind of subjective. Just depends on how you interpret it. All right, so what would you predict for the average attendance for a team that's 2 standard deviations above average, so a positive z-score of 2? Well, we predict the z-score for the y is equal to the correlation coefficient times the z-score for the x. You could also flip the x and the y because the correlation is going to be it's unitless. It also doesn't matter the direction because of the commutative property multiplication when we take the products of z-score. So it doesn't matter what direction we go in. If we're making a model with the slope, then it does matter. Remember the tale of 2 regressions. Okay, so in this case, we could do, it's going to be our correlation coefficient times 2, a positive 2 for our 2 standard deviations above the mean, which is going to give us a positive 1.0658. If a team is 1 standard deviation below average in attendance, what would you predict for the number of games the team has won? So again, we're just going to do negative 1 because it's 1 standard deviation below to get a z-score of that value there. All right, so for 42, we want to write the equation of the regression line. So we're predicting attendance, so it's going to be the attendance hat is equal to our slope, which you said was 431.2, times wins minus our y-intercept, which is 6,760.5. Estimate the average attendance for a team with 50 wins. So we're just going to evaluate that and plug in 50 there. Whenever we put that in the calculator, I'll save you watching me put it in the calculator. It's going to be 14,805. Interpret the meaning of the slope of the regression line in the context. So our slope is going to be 431.22. So for every additional win, on average, we are predicting that we're going to increase the attendance, the average attendance, by 431.22 fans. So our model predicts for every additional win a team has in their season, then the average attendance will increase by 431.22. All right, in general, what would a negative residual? So negative would mean it was less than predicted. So that would mean that a team had a lower average attendance than our model would predict, which is not what you would want. That means you're winning a lot of games, but no one's showing up for them. The San Francisco Giants, 2010 World Champions, were not included in the data because they're a National League team instead of the American League team. So during the 2010 regular season, the Giants won 92 games and averaged that number of fans at their home games. Calculate the residual for the team and explain what it means. So what we're going to do is evaluate our equation for 92. So let me clear this out real quick. So I'm going to take my slope of 431.22 multiplied by 92, and then I'm going to subtract from that 6,760.5. Okay, so that's going to give me my prediction from the model. Now, if I want to find the residual, the residual is the actual minus the predicted. So the actual they said was 4,736 minus the prediction, which is right here, and that's going to give me a residual of positive 8,824.66 on average. So essentially that was what we got from plugging into our equation, and then we subtract that from the actual to get this value here. Now, typically we would round, but in this case, because we're dealing with an average, it is possible to have an average attendance with less than a whole person, right? Because it's an average, and averages can be calculated to have decimals. So most of the time, if it didn't make sense, like you can't have half a person, but you can have on average, and the average size American family was like 2.5 children. You can't have an average of a decimal, but you can't have 2.5 children. Okay, even if you really don't like your little sister, she's still like a whole person. I know, it's so frustrating. All right, 48. Success in college. So colleges use SAT scores in admission process because they believe the scores provide some insight on how a high school student will perform at college level. Regression analysis was computed on using the SAT to predict the GPA. So they took students, they looked at their incoming SAT and their GPA that they had at the end of college, and they tried to see if there was a correlation between the two. And not only the correlation, but they created a regression line to be able to model out and predict their GPA, which would be like their success in college, their college GPA based on their SAT. So write the equation of the regression line. So down here, coefficient SAT, the coefficient's talking about the y-intercept. So that's going to be the part that goes back here. And then the SAT, that's going to be the one that goes with the SAT variable, which is the slope. And our dependent variable is our GPA. So hopefully you're figuring out how to analyze regression analysis. And we put the hat over the GPA because we're predicting the GPA. Explain what the y-intercept of the regression line indicates in the context. So the y-intercept is whenever the GPA or the SAT is 0. So when the SAT is 0, that's going to get rid of this whole term here, and then we're just going to be left with the y-intercept. So that's where it crosses the y-axis, right? So if we had a student who had a 0 on the SAT, we would predict they would have a negative GPA. So our model would predict a student with an SAT score of 0 would have a negative GPA of negative 1.262. Now, often the y-intercept doesn't make sense. Is it even possible to have a negative GPA? No, nor is it possible to have an SAT score of 0. At least I don't think. I've never tried that hard, honestly. Anyway, life goals. So I don't know. So it's not possible, but it's still important to have that because it makes our model work. And the reason why these are so outlandish is because it's extrapolation, right? So in all the data set of all the students that they never had a student with a negative GPA, and they never had a student that had if we're looking at domain, we'd be dealing with SAT score. So they didn't have any students that had an SAT score that were going to college at least with a 0. Okay, so this is clearly extrapolation. Anyway, keep that in mind. Interpret the slope of the regression line. So our model predicts for every additional point you score on the SAT, your GPA or predicted GPA would go up by the slope. So our model predicts for every additional point scored on the SAT, the student's GPA would increase by 0.00214. Okay, cool. 48, last slide, almost done. Not too bad on time. All right, success in college. Moving on. Predict the GPA of his freshman who scored a combined 2,100. So I'm not really familiar with how they score the SAT because we do the ACT in Oklahoma, but you get the idea. Just plug it in here, multiply it by slope, subtract the y-intercept, and it'll get your value. So an estimated GPA of 3.232. Based on the statistics, how effective do you think the SAT would be in predicting academic success during the first semester of the freshman year at this college? All right, well, if we look over here, in order to find the strength, remember we could take the square root of this value, the 0.221, and that would be like 0.4, 0.5. But we actually want to interpret it using the r squared. So the r squared, remember the coefficient of determination, tells us the amount of variation that can be removed from our y variable, which is GPA, by looking at our explanatory variable. So in this case, only 22.1% is rough, right? Only 22.1% of the variation in the GPA can be accounted for by the model with using the SAT. So the remaining Let's see, the remaining 77.9% of all the variation in GPA is based on something else. We don't know what it is. We don't know. So I don't necessarily think it'd be very helpful or effective, it's kind of the same thing in here, in predicting the GPA, as the model only removes 22.1% of the variation in the student's GPA. I would want a stronger association or stronger correlation, because we're talking about linear associations. But maybe this is the most helpful one that they can have, because there's just a lot of other factors at play. And hopefully one of those other factors was more helpful. I don't know. As a student, would you prefer to have a positive or negative residual in the context? So with residuals, would you rather have a higher response variable than expected or a lower response variable than expected? So a response variable is GPA. I would rather have a higher GPA than what my SAT would suggest. So I'd rather have a positive. That would mean that I had a higher GPA than predicted by the model from my SAT score. And that is it. So not too bad, coming in on time. We just have the rest of the assignment, so try to make the lecture pretty short, and half of it we're just going through the assignment anyway. So finish the assignment, and we will take a practice quiz pretty soon. So see you guys. Have a good day.